Welcome to an exploration of one of the most fascinating phenomena in nanoscale fluid dynamics, hydrodynamic slip. At the nanoscale, fluids behave in surprising ways that challenge our classical understanding of fluid dynamics. Let's start by understanding the classical no-slip boundary condition that dominates macroscale fluid dynamics. In classical fluid dynamics, we assume that fluid molecules directly touching a solid wall have exactly zero velocity relative to that wall. Here we see the classical picture. Fluid particles at the wall are stationary while those above flow. This creates a velocity gradient near the surface. Mathematically, we express this as velocity v at the wall, position y equals 0, is exactly 0. The no-slip condition has been validated countless times in macroscale applications, from pipes to rivers to aircraft wings. But what happens when we shrink down to the nanoscale? The physics changes dramatically. Let's pause and ask ourselves, why would fluid behavior change just because we're working at smaller length scales? The answer lies in surface-to-volume ratios. At the nanoscale, surface interactions become dominant compared to bulk fluid properties. Compare a macroscale cube to a nanoscale cube. The surface-to-volume ratio increases dramatically as we shrink, making surface interactions far more important. To quantify slip at the nanoscale, we introduce a crucial parameter, the slip length. The slip velocity at the wall equals the slip length b times the velocity gradient at the wall. The slip length b tells us how far into the wall we'd need to extrapolate the velocity profile to reach zero velocity. This diagram shows how we extrapolate the velocity profile below the wall surface. The distance to zero velocity is the slip length. In the classical no-slip case, b is 0. For perfect frictionless slip, b would approach infinity. Carbon nanotubes provide the most dramatic example of hydrodynamic slip in action. A carbon nanotube is a cylindrical structure made of carbon atoms arranged in a hexagonal lattice. Water molecules flow through with remarkable speed. Experiments show that water in carbon nanotubes exhibit slip lengths ranging from 20 to 200 nanometers, which is enormous at this scale. A typical value is around 50 nanometers for water in single-walled carbon nanotubes. This slip leads to flow rates that are 100 to 10,000 times faster than classical no-slip theory would predict. What physical mechanisms cause this dramatic slip behavior? First, the interaction between water molecules and the smooth graphene surface of carbon nanotubes is very weak. Water molecules interact weakly with the ultra-smooth carbon surface, unlike rough surfaces where molecules get trapped in surface irregularities. Second, carbon nanotubes have atomically smooth surfaces with no defects or roughness to trap fluid molecules. Third, the hydrophobic nature of graphene means water molecules prefer to interact with each other rather than with the wall. Let's quantify exactly how much the flow is enhanced by slip. The flow rate with slip equals the no-slip flow rate times 1 plus 4 times the slip length divided by the tube radius. Let's do a numerical example. Consider a nanotube with radius 1 nanometer and slip length 50 nanometers. The enhancement factor is 1 plus 4 times 50 divided by 1, which equals 201. The flow is over 200 times faster. This bar chart shows the dramatic difference. What would take 201 seconds with no slip takes just 1 second with slip. Let's use the driving car analogy to build intuition about slip. Imagine driving on a normal road. Your tires grip the surface, there's friction, and you can control the car. Now imagine the road becomes ultra-slick ice. The car glides with minimal friction, moving much faster with the same push. In macroscale fluids, it's like the normal road. Molecules at the wall experience friction and stick to the surface. In nanoscale flows with slip, it's like the icy road. Molecules glide past the surface with minimal resistance. Let's see how the famous Hagen-Poiseuille law changes when we include slip. The classical Hagen-Poiseuille law says flow rate equals pi r to the fourth times pressure drop divided by 8 times viscosity times length. This classical formula assumes the no-slip boundary condition at the tube walls. With slip, we multiply by the enhancement factor of 1 plus 4b over r, dramatically increasing the predicted flow rate. Let's do a real calculation for water flowing through a carbon nanotube with 2 nanometer diameter. Given, nanotube radius is 1 nanometer, slip length is 50 nanometers. Tube length is 1 micrometer and pressure drop is 10 megapascals. Viscosity is 0.001 pascal seconds. With slip, we multiply by 1 plus 4 times 50 divided by 1, giving enhancement of about 201 times. The result is dramatic. Flow is 201 times faster than classical theory would predict, making such membranes highly efficient. Molecular dynamics simulations reveal fascinating details about slip at the atomic level. Molecular dynamics simulations show individual water molecules near the carbon nanotube wall. Notice they maintain finite velocity even at the surface. Water molecules form somewhat ordered layers near the smooth carbon surface, but unlike in macroscale flows, these layers maintain velocity. An important question: do all materials exhibit slip at the nanoscale? The answer is no. Slip is most pronounced on smooth, hydrophobic surfaces, like graphene. Rough or hydrophilic surfaces show much less slip. Understanding nanofluidic slip enables revolutionary applications. One promising application is water desalination using carbon nanotube membranes that allow ultra-fast water flow while blocking salt ions. Water molecules flow rapidly through nanotube pores due to slip, while salt ions are blocked. This could revolutionize desalination efficiency. Nanofluidic channels with controlled slip can enable precise drug delivery at the cellular level. The high flow rates enabled by slip could be exploited for energy harvesting from pressure-driven flows in nanochannels. How do scientists actually measure these tiny slip lengths experimentally? One method measures the flow rate through nanochannels under known pressure. Enhanced flow indicates slip. We extract slip length from the ratio of measured to theoretical flow rate using this formula. Another method uses a surface force apparatus to measure friction between surfaces separated by a thin fluid film. Atomic force microscopy can measure hydrodynamic forces on a probe tip moving near a surface in fluid. A major challenge is that even tiny amounts of contamination or surface roughness can dramatically affect slip measurements. There's a deep connection between slip and the Knudsen number, a dimensionless parameter. The Knudsen number equals the mean free path lambda, divided by the characteristic length scale L. When the Knudsen number is small, continuum assumptions and classical fluid dynamics work well. As the Knudsen number increases toward 0.01 to 0.1, slip effects become significant and must be included. Interestingly, the slip length often scales approximately with the mean free path of the fluid molecules. Slip length varies dramatically depending on the surface material and fluid combination. This chart compares typical slip lengths for water on different materials. Glass shows about 5 nanometers, silicon about 20, and carbon nanotubes up to 50 or more. The general rule is that hydrophobic, water-repelling surfaces show much more slip than hydrophilic, water-loving surfaces. Even nanoscale roughness can dramatically reduce or eliminate slip by trapping fluid molecules and surface irregularities. Slip length also depends on temperature in interesting ways. Slip length often shows exponential temperature dependence with an activation energy E sub A. Higher temperatures generally increase slip because molecules have more kinetic energy to overcome surface interactions. This graph shows how slip length typically increases with temperature, following roughly exponential behavior. However, viscosity also decreases with temperature, so the combined effect on flow rate is complex and material dependent. Slip isn't limited to water. Let's look at other fluids in nano-confinement. Liquid argon, often used in molecular dynamics simulations, shows significant slip on smooth surfaces. Organic solvents like hexane or decane can exhibit even larger slip lengths than water on hydrophobic surfaces. Even molten metals can show slip when flowing through narrow channels, though the physics differs from molecular liquids. Generally, organic solvents show more slip than water, which shows more slip than ionic liquids. In aqueous solutions, the electric double layer near charged surfaces affects slip. Near a charged surface, ions form an electric double layer. This structured region can modify slip behavior. Charged surfaces typically reduce slip because ions and their hydration shells interact strongly with the surface. The zeta potential, measured in electrokinetic experiments, tells us where the effective slip plane is located relative to the surface. Let's work through a complete practical example with real numbers. Suppose we're designing a carbon nanotube membrane for water filtration. We need to predict the flow rate. Given, nanotube radius is 0.7 nanometers and length is 10 nanometers. Pressure drop is 50 megapascals and slip length is 40 nanometers. Tube length is 1 micrometer and water viscosity is 0.001 pascal seconds. Using Hagen-Poiseuille, the no-slip flow rate is pi times 0.7 nanometers to the fourth times 50 megapascals divided by 8 times viscosity times length. This gives about 1.5 times 10 to the minus 19 cubic meters per second for no-slip. With slip, we multiply by 1 plus 4 times 40 divided by 0.7, giving an enhancement of about 230 times. The result is dramatic. Flow is 230 times faster than classical theory would predict, making such membranes highly efficient. Let's explore where current research on nanofluidic slip is heading. Researchers are exploring how to control slip by patterning surfaces with alternating hydrophobic and hydrophilic regions. Two-dimensional materials like graphene sheets create the ultimate smooth surfaces, potentially enabling even larger slip lengths. Understanding how slip couples with electrokinetic phenomena opens possibilities for ultra-efficient pumping and energy conversion. Biological membrane channels may exploit slip-like phenomena, and understanding this could inspire biomimetic designs. Multiple research directions are converging: surface chemistry, 2D materials, electrokinetics, and bioinspiration. The field isn't without challenges and ongoing debates. An important question that took years to settle: is slip real, or just an artifact of experimental uncertainties? The answer is clear now. Slip is real and has been confirmed by multiple independent experimental techniques and simulations. However, the exact values of slip length for specific systems are still debated, with different groups reporting different numbers. Surface contamination, even at trace levels, remains a major experimental challenge that can obscure true slip behavior. Different studies sometimes report slip lengths differing by a factor of 10, highlighting the challenges in making precise measurements. Let's summarize the key concepts we've explored about hydrodynamic slip. First key point: at the nanoscale, the classical no-slip boundary condition breaks down due to weak fluid surface interactions. Second, the slip length parameter B quantifies how much the flow deviates from classical predictions. Third, carbon nanotubes show extreme slip with lengths up to 200 nanometers, enabling flow rates hundreds of times faster than expected. The enhancement formula shows flow rate equals classical prediction times 1 plus 4 B over R. In conclusion, hydrodynamic slip is a fascinating phenomenon that challenges our classical understanding of fluid dynamics at the nanoscale. By understanding and controlling slip, we can create more efficient nanofluidic devices for applications like water purification, energy harvesting, and biomedical research. This is a fascinating area of ongoing research with tremendous potential for innovation and discovery.